Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.5: State and Path Functions. State functions depend on the state of the system. For example, pressure, volume, temperature, and entropy are state functions. Internal energy, enthalpy, Helmholtz energy, and Gibbs energy are also state functions. The number of moles is also a state function. The differential of a state function is an exact differential. Exact differentials can be integrated given the lower and upper limits of the integral. The cyclic integral of an exact differential is always zero. For example, internal energy U is a state function, and we can calculate delta U, the change of internal energy, as the integral of du from the initial state to the final state. And this integral is equal to the final internal energy minus the initial internal energy. The cyclic integral of du is always zero because u is a state function. As long as a system returns to its original state, then the final internal energy is equal to the initial internal energy. Delta U is zero for any cyclic process. We can replace U with any other state function in these two equations. For example, we can examine the pressure. We know the change of the pressure is just the integral of dP from initial to the final, or it's simply final pressure minus initial pressure. We do not have to know how the pressure changes from 1 bar to 2 bars. We just know delta P is 2 bars minus 1 bar. That's it. The cyclic integral of dP is zero. It's just because after the system undergoes a cyclic process, the system returns to its original state. Therefore, the final pressure is the same as the initial pressure in a cyclic process. The change of a state function depends only on the initial and final states of the system. It does not depend on the path this system undergoes between the initial and final states. Path functions depend on the entire path of a process. That means the value of a path function does not only depend on the initial and final states of the system, it also depends on the path that connects the initial and final states. Two examples are heat and work. They are both path functions. The differential of a path function is an inexact differential. When we write out inexact differential, we need to have a bar through this differential operator d. So you always see this d with a strike through. An inexact differential cannot be integrated given only the initial and final values of the variable. We have to know the information about the entire integral path. For example, there's an equation for expansion work, negative integral p external dv. If we only know the initial and final states of the system, we cannot compute the value of work. We have to know how this external pressure changes through the entire compression or expansion process. This P external can be a constant. Well, it can be like two different constants. In step one, you have a constant P external. In step two, you have another P external. Also, P external may change in the entire process. The cyclic integral of an inexact differential is often non-zero. Even if it's a zero, usually it's just due to coincidence. Here's an example. After 1 mole helium, undergoes a series of steps of expansion and compression and returns to its original state. That means the initial PVT are the same as the final PVT. The cyclic integral of dq with a bar and dw also with a bar through this d, they are often non-zero, even though the cyclic integral of du is always zero. We do know du is equal to dw plus dq. Then how can the sum of two path functions be a state function? Well, here's a simple example. The integral of y dx and the integral of x dy are both path functions. Their values cannot be determined given only the initial and final values of x and y. Here's the example. If I tell you the initial values of x and y are 1 and the final values of x and y are 2, how can you integrate this y dx? We don't know because y may change between 1 and 2. It may be a function of x, it may be a constant. We do not know. Therefore, we need more information to calculate this integral of y dx. For the same reason, we need more information to calculate the value of the integral of x dy. However, if we sum up these two path functions, the integral of y dx plus the integral of x dy is actually the integral of dxy. This is based on a rule, the product rule in calculus. dxy is y dx plus x dy. Therefore, the sum is simply the integral of dxy. Therefore, it's simply xy plus a constant. Now, if we have the initial values and final values of x and y, we should be able to get the value of the integral. It's simply 2 times 2 minus 1 times 1. We get 3. Now let's look at a graph. So now, if we have a curve over here, let's say this is a function of x, y is a function of x, and this curve represents that function. Then how do we integrate y dx? We do need to know how y changes with x when x goes from 1 to 2. So the integral of y dx is this area under the curve, and the integral of x dy is this area, okay, to the left of the curve. We do not know this integral or this integral. However, we can calculate the sum of these two integrals. Well, it's pretty simple. The sum of these two integrals, if you look at it, it's this larger square, 2 by 2 square, minus this smaller 1 by 1 square. Therefore, it's simply 3. Again, this integral is a path function. This integral is a path function. But the sum of these two path functions is a state function. Y dx by itself is inexact differential. X dy is another inexact differential. But x dy plus y dx, we get dxy, the exact differential of xy. So it's possible for the sum of two inexact differentials to be an exact differential. For the same reason, du is equal to dq plus dw. du is an exact differential, but dq and dw are both inexact differentials. And also we know delta u is equal to q plus w. Although q and w are path functions, they depend on the path of the process. However, delta u depends only on the initial and final state of the system.